All right. Okay, hey everybody, welcome to today's Delegate Assembly. Today we're going to have Meg Schwamb give a presentation that's part of the lead up to the Solar System Science Collaboration Sprint that's happening next week. So Meg is here. I'm just going to do some of the first usual announcements and then we'll turn it over. As usual, this is a normal delegate assembly where the first hour we'll spend in a presentation, and then at around 10 a.m. or whenever the presentation's done, we will come back to this slide. We will decide if we want to have breakout rooms. These are things that anyone who's here can suggest a breakout room. There's some initial suggestions already here in the table. We'll set up the breakout rooms at that time, and then we will also have time to hack together, or you can get your questions answered or get help with anything you're working on related to DP0. So a couple of announcements today. The first one is, in order to get today's notebook, you can go to, I'll put this in the chat for anyone who's just joined. You can go to this GitHub repo. And then also in the notebook aspect, open a terminal. And remember, the way you do that is this would be the landing page when you first enter the notebook aspect. Go ahead and use a large container for today. I think we're going to be doing a bunch of plotting. And when you land in the notebook aspect, start up a terminal. It's a regular terminal, and you can use any subdirectory you want or the main home directory. And then you want to do a git clone statement there. It will get everything that you need for today. It's doing it. And now you have a new DP0.3 example notebooks folder. It has today's notebooks in it, and you can navigate there. For me, I put it in the My Notebooks directory, but yours might be right in your home directory. DP0 example notebooks, and there they are. You can open them from here. Douglas, your hand is up.
Oh yeah, yes. Can you also add the git clone to the chat window, please?
Yes.
Thank you.
For your convenience. Paste it. There we go.
Great, thanks.
You're welcome. All right, so that's the process for getting today's notebooks. So that is there in the chat for you. I think just two announcements today. One is that the revised timeline for early science with Rubin Observatory, that's the timeline for commissioning and the rest of the data previews up to data release 1. That was just released this morning. So Rubin Tech Note 011 is the place to go for like the full description of everything that's happening over the next couple of years. And you can start with this post in the community forum that has the useful links for you to that tech note with the full description, and then also with the link to the citable DOI, which is the thing everyone needs for their grant proposals. So that is there for you. It's ready. And if you have any questions on that, just head over into the forum. You can post a new question as a new topic in the early science category, or let us know later today in the breakouts time. We can try and get those questions answered. Second announcement is just for the future DP0 virtual seminars that are coming up. Next week, we'll have another delegate assembly that will review the phase curves tutorial. 2 weeks from now, it's a stat club, the usual drop-in session time. 3 weeks from now, Friday, November 10th, is a special delegate assembly where we'll have a special guest, Jen Kotler from Space Telescope, who's built or helped to build the Notebooks for All repo, is going to give a presentation on accessibility for notebooks. And then the breakout time will be basically a little hackathon where everyone can bring their own notebook, and we'll try to implement some of the things we just learned. So that's lots of fun stuff coming up in the next couple of weeks. And I'm just going to pause again for any questions about getting today's notebooks or any of the announcements. All right, well, Rubin staff are here. We're monitoring the chat while Meg is speaking, so don't feel like you have to wait in order to ask your question. As soon as you have an issue, just pop it in the chat or raise your hand, and we'll try and get to that as we go. And I'll hand it over to Meg.
Cool. Hi, I'm Meg Schwamb. I'm a senior lecturer at Queen's University Belfast. I'm the Solar System Science Collaboration co-chair. So if you're interested in solar system and not a member, do consider joining. We're a pretty friendly bunch. So if I thought I would sort of go through some of the things that I want to plot, because I felt like there are lots of great notebooks, but I was like, what is it that I want to do in the RSP if I have the data today? And so I don't have a lot to show, but I wanted to show just the examples that I'm doing and especially the joins, because joins is where I get stuck, particularly doing any of these things in these sort of ADL queries. So what I've done is I basically was like, cool, this is all online. I want to test the system of what would I do at 10 years if I could plot all of the detections, because that's the distribution I want to look at, right? If I'm interested in comparing to population statistics, which is secretly what I theoretically care about some days. And so the two notebooks sort of go through plotting that for the KBOs or TNOs and the MBAs. And I think the challenge is that the TNOs is actually much easier because it's only roughly about 40,000 objects, where the MBAs is in the millions, right? It's roughly about 5 million detections. And so they definitely, again, scale in different ways. And so the fun thing is if you just start running the notebook, the fact that pretty quickly these, especially in the large container, it all comes back and can plot is pretty exciting. I also just want to highlight, especially for my people that are playing around with this, that I didn't really understand all the different ways of viewing data because I didn't need to when there's only about 4,000 KBOs. I plotted them as scatter plots. And you can't do that with 40,000. And so I just wanted to show a couple examples of ways you could show the data. I only do sort of 2D histograms of sorts in the data set, but I also just want to highlight some that I just threw into my notebook, and I'll copy the commands if people are interested and show you some more seaborn, which sounds like it's an idea or suggestion people are going to talk about. So all I'm doing is the same things that everyone's seen before in all the notebooks is the tap queries in the first query, getting the tap service connected and then querying. And so the difference here in my query is that a lot of the queries you see in the examples are a set range of objects, but instead I want a set range of orbits. And so for here, I'm merging the MPC orb because that's going to have the orbital parameters with the SS object, right? The detections. And so it's the join in here that's the most important, is that it's again, right? Using this, I can confuse it, but that's all right. It's already been run. And linking these here, right? And so the join is the most important here because it's saying, okay, great, it's taking these two, right, in the 10-year catalog, right, linking these to the orbits catalog from the MPC and the sort of SS objects, right, the detections together. And then making these restrictions on orbits, right, that I want eccentricity to be greater, less than 1, I don't want hyperbolic, I don't want parabolic, those are not hybrid objects or TNOs. And then because there is no semi-major axis column, doing the requirement that we have semi-major axis greater than or equal to 30, with also perihelion greater than or equal to 30, because I'm cutting out the centaurs. And so the idea is that this is the kind of query I think many people will be building in some different ways, of that you're going to be pulling subsections of the population that you want to be doing something with. Again, it might have additional things like number of detections if you want to do colors, but that I just wanted to highlight that I think there's been lots of great notebooks, but not necessarily one that's like, here, grab me everything of this population. So all I'm doing is querying all I'm doing here in this line here, in this box, is pulling all of the information, right, from the query into a pandas table, and then creating a semi-major axis column, because I want to plot in terms of A, because cometary orbits are great, but when you're doing, bound objects, you don't necessarily need to do it. So I want a semi-major axis. And then I just wanted to see how many objects there were. And so it's not quite, so, it's coming up with about 23,000. Take these numbers with a grain of salt. They are made some assumptions in running what is now called Circa, the code that the simulator that helps create this. And so these numbers might change a little bit by a factor of 2 or so. from that as we change some of the assumptions that went into that. So you can definitely quote these numbers in your proposal, but I quote a range of a factor of 2, at least. So it's somewhere in the round of 20,000, 40,000 objects that'll be discovered by LSST. So all I wanted to do is, again, do some comparisons with the truth table of what's total in the population / what's in the minor planet center. Part of what was confusing for me, especially, which is I learned after reading the documentation and then being reminded, but didn't quite get it when reading it, was that the MPC orb table is a truth table in the sense of it's everything that was simulated. Where I thought it was a truth table and that it was, here's all the orbits for the things we inputted that you detected, but it's actually everything in the simulation. So you'll notice it's huge. And you're like, but wait, it's supposed to be only most of LSST is going to dominate and find or detect most of the TNOs. So this should be the same. So it's not, because this is using everything that's in the simulation. So something that I didn't grasp initially, that, if the commands I'd want to do to plot everything that's known in the minor planet center compared to what just LSST found, you're going to get sort of a little bit of a different answer now using DP0.3. So just something to be aware of, because I looked at that and went, why is that different? And so it makes sense now that this is a truth table of everything simulated, not necessarily, or of that sense, not necessarily, quote, the things that LSST would find plus what's already in the MPC today. So all I'm doing in this next step is that I was like, great, I got a query to work. Does it give me the right things? And so just getting it to come out with those observations with the table. And then all I decided to do was just look at the different distributions in different ways. And so one of the nice ways that I sort of do this, or at least been playing with the various DP0.3 iterations on the Solar System Science Collaboration Jupyter Hub, and now on the RSP, has been with the seaborn plotting package. And so I have them in the next tab. And so all I just want to highlight is that seaborn's really nice in that it's built on matplotlib. So matplotlib commands that you want to do work, but it's very powerful in being very good at handling pandas data frames, whether you like pandas data frames or not. But for plotting, it's probably pretty good to convert things to pandas data frames. But also the fact that the gallery is really nice. So if you're not used to, what a boxen plot is, you can look at it, look at the examples, and so pretty quickly figure out what you want. And so if you haven't used Seaborn before, I really do recommend looking at it. And that the tutorials have been really great as someone who hasn't really only used it basically for plotting things when it's come to LSST simulated data. It's been really helpful. And that it really just comes with all these different ways, again, of doing that. So again, a scatter, a bivariate plot, right? A scatter plot with, again, contours, right? Heat maps, all very useful things, right? That I wouldn't necessarily think that I needed, right? But having these sort of really nice quick graphics, and generally they all look very good. These are all basically built. The default color schemes are built for, again, thinking about people with visual impairments and sort of optimizing for best colors. And so it's really a nice, powerful package. Again, that you will feel a little bit familiar because it has the engine underneath it being matplotlib. So one of the nice plots you can make is these sort of hexagonal histograms or heat maps, right? And then what I like is that it gives me, or you can enable plotting the 1D distributions on the sides. And so all I'm doing here is taking the population from the discoveries from LSST and plotting them up. And so just again, for those that are familiar with the Kuiper Belt, I want to see those fingers, those resonant fingers from the resonator populations. And so that we're seeing that right here. So we're seeing sort of these fingers reaching out that are objects in mean motion resonance with Neptune. So orbiting an integral number of times, right? That of Neptune. And so again, you can see it sort of pop out in its distribution. You can add color bars to this as well. I just used default configuration, which doesn't provide one for this this plot, I guess, by default. But I find, again, that sort of 2D histogram, really breaking it from the 2D histogram down into the sort of 1D really helpful. And again, you can see what we would expect, right? There's more things at lower eccentricity, but there is a distribution. And again, you can see those sort of, again, the resonance is sort of popping out in semi-major axis. And so what I expect to see is kind of there. I can see the scattered disk, etc. I don't always find this plot the best way of visualizing it, but I find that it's sometimes helpful to see the contrast compared to the heat map 2D histogram. And so again, all I'm doing is expending my different commands to do that. So, right, starting down in these different colors, right, as well. And so the join plot is again giving me this sort of, again, hexagonal histogram, and then I have these hist plots, which are the heat maps. And so here's just showing semi-major axis versus eccentricity. Again, with this one comes automatically with a color bar. I've just changed to, again, not off the default. I wanted to use something slightly different than the default color. So here I'm using the heat color bar scheme. And so again, you can sort of see those resonant fingers popping out. And then same thing, if we look at some major axis versus inclination, it's what I would have expected for the Kuiper belt. So again, just thinking about the fact that really quickly with seaborn, I get the plots that I like out of it. So this is really the highlight I wanted to show you, but also that, again, you know, that you can easily pick out your subsets with pandas data frames and filtering. So I already did my query, but now I want to zoom in between that 30 and 70 AU where the bulk of the Kuiper belt is, or at least the bulk that's not the scattered disk. And so I don't have to redo my query. I'm just filtering on my pandas data frame. And so creating it, might always do this the right way, but I create a temporary data frame off of that query. Not always the best, the filtering, not always the best way to do it, but that tends to be the way I do it most times. And then the idea is that, again, making the same plots. And so the idea is that just now I've got a slightly better view, right? Because I've cut off the scattered disk. And so again, these resonant fingers pop out much more in the data. So just to highlight, these are, again, I think ways that we will explore the data set as it comes in with these numbers we're getting. And so for me, this was kind of new because I used to just plot this up as a scatter plot and be done with it. And so actually thinking about a little bit more about what one needs to do with the data set. So I did the same thing with the minor planet center, so you can compare these two, and it's the same thing, it's just more objects. And it's because it's the full simulation. But just to highlight, that's all I'm doing is comparing the two, which is what I might want to do to start looking at some of my biases of what LSST found compared to what's fully in the minor planet center. Maybe at the start of the survey, right, where the start of the survey in the first few months, it may not be dominated by what's LSST is discovering. So again, same thing, just zooming in between 30 and 70 AU. So these are just some of the example plots, at least for the TNOs I wanted to show. The other notebook I'll quickly go through has the same things for the asteroid belt. A couple of things I just wanted to show. I don't have it in the notebook on GitHub, but I wanted to show really quickly is that you can redo these queries and that these other some plots that you get from seaborn can be really powerful. So all I'm doing is redoing my query. It's just now I'm doing this. I'm just cutting objects less than 1,000 AU, objects that are greater than 1,000 AU in centimeter axis, trying to remove most of the comments. And so if I do a violin plot, which is again looking at the distribution, you immediately see there's something right out here, 500 AU. And all I'm doing here is asking to plot a violin plot, plotting that distribution of A. And so the nice thing about violin plots is that, again, I don't know lots about them, but it's giving you the shape of the distribution, right? So showing you, right, what it looks like in that one dimension, right? And so it's really helpful understanding where the distribution is and where some of the outliers are. This one is eccentricity. You can, again, there's ways to combine these plots into one. I have a student, Brian Rogers, who did a little bit of work of trying to create a little bit of package that helps do that for some of these distributions that we're going to hopefully sort of rework a little bit for DP0.3 that we can, again, help people use this. But just to highlight that the violin plots, lots of plots in seaborn and different ways of showing it can reveal different things. So immediately, right, it wasn't very apparent in the inclination plot that there was an object with an inclination of 175, but immediately pops out of it here. Right? There's something that most of the things are less than 50, but there's clearly something sitting up there. It might be a contaminating comet. I haven't poked at it deeper, but that didn't immediately pop out at me at the histograms. And so I just wanted to point that out, that there's these different ways of interrogating the data. And so again, the way I really recommend to learn how to do this is then the way I just did it, because I always forget, is to go to the seaborn page, go click on the example, read through it, and copy and paste from the command. And so the nice thing is it gives you lots of examples of how to do it, and then, you know, to look at it. And so these are just some of the plots that I've found really helpful. And so again, right, I can do the same thing by cutting my orbit with filtering. And then I noticed, oh, by the way, that some of those, that object of 500 AU went away, right? Because I am forcing it to be less than that. And then you can do the same thing in eccentricity, looks a little bit better, less eccentric. And then, oh, look, that inclination rate, that object that was really high, I know it's much, it's outside at least it's outside of the main part of the Kuiper belt because it's not showing up here. But I do have an object with an inclination of 60, so that might be interesting. So the nice thing is that I think is the histograms are great, the 2D histograms are great, but sometimes they're not going to find the outliers as quickly as looking at violin plots and derivatives of that. Where immediately you start seeing the outliers, but you might not really get as much information about the distribution looking at in these 1D formats. So I just want to highlight that because I found by poking around at DP0.3, looking at some of these violins and plots and derivatives. So like the Boxen plot is very similar, but it's putting these little boxes instead in the distribution. So it's showing you the data in a different way, right, than this. They're very similar, but they are sort of packaging it slightly differently. And same thing, this is just the box plot, which is showing you that more with sort of the error bar like things and then putting the real outliers as individual points. So again, showing you the distribution. So I just want to highlight this because it depends on how your brain works, I think, as well as your eye, but that these I think are also be really valuable in terms of figuring out what's going on in terms of these distributions of what's interesting without having to go to machine learning. There will be things for machine learning that you want to do as outlier detection, but I think some of these plots are really useful. So what I really recommend is go look at Seaborn because that's how I've been figuring it out is by looking at what things seem relevant, playing with it, and then seeing what's the best way for me to find outliers or interesting things. And so what I've kind of gone through is exactly what I have in the MBAs. I don't know if anyone has any questions on the TNO notebook or in general. Yeah, go ahead.
Yeah, I had 2 questions from the TNO notebook. The first one, I think I might have missed when you explained the violin plot, what the x-axis is.
It's the distribution. So it's some number of your distribution, right? So it never plots exactly what it is, but it's showing you sort of, again, your probability function. So you don't quite get a number for it, at least in Seaborn, but it's showing, it's sort of supposed to be that the shape of your probability distribution based on your what you have, right? So it's supposed to be like most of the objects here, right? Most of the objects are centered at lower, in this one is eccentricity at lower eccentricity. So it's kind of just giving you a general shape. So it's not a plot to necessarily measure your, at least the way Seaborn does it, is it's not giving you the value, right? You may be able to try to force it to give you more of an x-axis, but from what I found is it's basically just trying to give you the shape of that quote probability distribution based on, or histogram, right, of your distribution in that one direction.
Is it always symmetrical, or do the positive and negative sides mean something?
It's always symmetrical.
So it's more for visualizing.
It's for exactly.
Just for the human brain.
Exactly. And so the idea is, I think, is that you're not using this to necessarily pick something out in terms of like what's going on here, but it gives you a quick sense of your outliers. Or again, the shape of your distribution, right? Because you can get the same means and medians, right, with a very different distribution. And so the point is you're like, oh, okay, most of my distribution's down here, but I have outliers up here. And so it's more for that visual sense of understanding how your data is distributed.
I see. It's like an option to histograms, but like rotated and made to mirror.
Yeah, and in one dimension, right? And so all I'm doing is taking eccentricity, right? In this case, I'm looking at it. And so and so it gives you some sense, right, of what's going on. Like here's semi-major axis, right? You're like, okay, great. Well, if I look between here, you can still see where most of the Kuiper belt is, and it kind of represents a little bit of what we saw in that 2D histogram. But what it gives is you the outliers much quicker. Okay. Right? I don't have to go searching for my outlier, right? Because when I do the full Kuiper, I was like, what's going on here, right? This is inclination. I know that there's only one data, there's not a whole distribution here. The fact that it's spiking as a line tells me it's like one data point.
Okay.
Which maybe this isn't the right plot, right? That I'd want to do instead of violin plot, you want to go down to doing like this plot here, right? Your Boxen plot, where now this looks a lot easier to go. It's only a couple of data points here, right? This is a 60 case, right? But it's showing you that sort of distribution. Breaking into box, right? So now you've got a sense, okay, great. It's only a couple of data points. Yeah. So now you have a sense of how many outliers you have as well.
Okay, that'll make sense. And the second question was whether you know if Seaborn can do interactive plots or whether it works with things like bokeh.
Yeah, so I don't think it works with bokeh. I think bokeh is different. I mean, it also has its own plotting ability, right? But yeah, you can do interactive plots because it's Matplotlib underneath it, so you can make them interactive.
Of course.
So that's the nice thing. It's built with Matplotlib underneath it. Sometimes it's hard to make it do things, but effectively, if you try around, you can kind of get it. You can find the combination of Matplotlib things that do work. But yeah, these are just some of the things that I hadn't realized. I was like, oh, there's so many objects. Like I'd never had to think about there's other types of plots other than scatter plots and 2D histograms. Like, why would I want this? But
Yes.
immediately, right, like I can pick out there's some weird object with that has some, it might be a comet, but it's like something that I might want to look at that I wouldn't have picked out in the 2D histogram that was sitting there, right, but wasn't being picked up. So I don't know if other science areas, especially using DP0.2, have sort of been exploring with all these different kind of plots, because it's something that I never learned, that I've kind of learned by looking at the seaborn documentation, right, of playing around and being like, what makes sense visually?
Yeah. Yep, heat maps are becoming essential for kind of all of us as we move into the big numbers era. Leanne, your hand is up.
Yeah, hi, thanks, Meg. It was great to see you using these violin plots. I've used them a lot before. And yeah, I agree with Melissa, heat maps, all these different ways of visualizing data are becoming more and more important. So just to note, and I put this in the chat as well, HoloViews. Okay.
Oh, you're breaking up again, Leanne.
Plots, they do this. I have a link in there to an example. Can you hear me better now?
Let's try with the video off, yeah.
Okay, I'll try this. Yeah, there's a local problem in this area. So basically, that contaminating comment in inverted commas, Meg pointed out, if you use interactive okays and HoloViews, it's set up code behind the plot that allows you to.
You're breaking up.
You can hover over the outlier point here corresponds to these rows in the category. Can you hear me?
It's real choppy.
Basically, if you use interactivity could allow you to do drill down, but then can allow you to hone in on those contaminants really rapidly and then do a subsequent follow-up analysis interactively. That's really, I put this in the chat. You can have a look in the chat.
Yeah, that's great to know, because that's definitely some of the things that, like, it's hard to get it set up on your own system.
It is,
so again, if those things are within the RSP, it's great, because then you can try it out, where like I really haven't tried bokeh very much because I haven't really gotten it set up very well. So
yeah, I mean,
it's definitely something I'd be interested to try.
Sure, I mean, you can try this out. There's examples there, or we could try to take your examples and set them up interactively and then show you how to enable drill down behind the scenes to get straight into your catalog and say, there's that pesky comment.
Yep, exactly. So that's all great things. So yeah, definitely something I will try.
Great. Let us know.
Maybe come back and report.
Great.
Any other questions for Meg before we pop on to the next notebook? Okie doke. Sounds like we're good to move on.
Cool. So it's all the same things in this notebook. So all I just wanted to show is that, and to me, and I waxed poetic on Twitter or X, or do we even acknowledge it's been what Elon has done to it? But the point being is that, like, this is hard. We've struggled with the sort of the Solar System Science Collaboration Jupyter Hub handling this, that just the sheer amount of numbers, and that if you run this, it actually runs quite fast. And if you know, this one ran in 3 minutes for me, or 4 minutes, right? And this is grabbing all the, you know, very large number of both what's in the Minor Planet Center as well as the detections from Rubin, right? And so just the fact that in Rubin, right, these huge number of detections, right, we're able to be grabbed very quickly. And so again, to show that the big bucket works really fast, right? Well, the large sort of node that we get, right, is really helpful. So the only difference here is just trying to really push the system by being like, can I grab everything from all the asteroids, which is what you'd want to do if you want to plot the orbital distribution for your paper, your thesis, etc. So it's the same thing I did before. It's just drilling down into the asteroids. and so the main belt asteroids. And so you can plot it. The point being, I just want to show is that it reproduces what you see. So again, doing the same thing of some major axis versus eccentricity. Again, that sort of note here where it's doing the join plot, that hexagonal histogram plus the 1D and then the two 2D histograms or heat maps. And so just again to point out that again, right, like this looks like what we'd see for the asteroid belt. So there's our Trojans, there's our main belt, right? We're seeing our populations, we're seeing the Kirkwood gaps, all that fun stuff. And just highlighting here, there's also just again, I didn't cut away all the comets, but you're at least seeing the shapes that we think we'd see. And so that's really the test of this, is just the sheer amount of numbers. Because I was like, great, can it do it? And so the fact is, it really can, right? The system didn't struggle returning back all those objects, which is great. That if you want in 10 years to do that with that many objects, it works now, which means it's going to work even more flawlessly, right, as the RSP gets further developed. So that's really just this notebook. It's exactly the same thing. Used maybe slightly different color schemes because I got bored, but the idea being is just I want just to allow people to be able to run it again with the join that would give you the right sort of the major axis distribution, so that you can actually see the same thing, that this is stuff we'd probably do at the start of the the end of the survey. After that last day, we'd want to be pulling all that data, right? So, or even at year 5, right? And so, or 2, because we'll have all these detections already in the first few years of the survey. We'll find most of the asteroids and TNOs. So that's really all I just want to highlight, was give an example and just again show that same thing of doing with the minor planets that are with even more objects. That really stresses the system that it runs right pretty quickly. And so that's all it is, just to show that in different ways. But again, give you something at that full scale of running it, right? And seeing that power that already, right, the RSP can handle that. That's kind of all I wanted to talk about, and just give some examples of what I've been playing around as, like what I would be doing if the data was flowing today.
Yeah, thanks, Meg. I'm running it at the same time, and I can notice it's taking a little longer, so I haven't been able to make the plots yet, but it is like over 4 million objects that get pulled over. Can we look at your notebook run times? I just want to see how long it took for you.
Let's go take a look.
It should say in the...
Yeah, so let's see.
Yeah, so query real fast, and then the first plotting. Oh no, wait, this is actually doing another query.
Yeah, this query took 4 minutes.
Ah, okay, yeah, that's where it's running for me now. Okay.
Yeah. So, I mean, but that's 4 minutes now, right? And so again, I think it'd be interesting to see if more people are doing that. How does that stress the system, where I ran it probably before people were trying to run the same command. But this is, I think, again, what people are going to be doing most of the time is running the full population, or a lot of people will be playing with different things from the full population. You're going to want your orbits and pull a subset of something weird with colors, but you're still going to want all the objects of a certain type to then look at that.
Yeah, I think almost 4 minutes for 13 million objects is
not bad.
Yeah, that's pretty good. And we have noticed sort of slowdowns when we're all like, there's 10 of us who do the exact same thing at the same time. Currently, it can slow a bit, but
that's pretty still minimal.
Yeah, it's still pretty.
And that's the point I wanted to highlight, was that I think a lot of examples are smaller subsets because you want to go really quickly. But I was like, okay, I want everything. Does that work? And it does, right? You can make these plots. And so before I started talking, I just reran them, and the fact that it executed, right? This is not an old notebook I loaded. I loaded the notebook, but I made it rerun everything.
Yes. Okay, this was just like an hour before-ish. Maybe it's today, though.
Yep. It was like half an hour ago. I was running it during it. So right at like 5 o'clock, it was starting to run. So.
Yes. Okay. Thank you. And more questions for Meg. Monitoring the chat. Oh, Leanne's just confirming that's good. Good query performance. Yeah. Yep.
Yeah. And so it sounds like HoloViews is a really good tool. It's not something I've had a lot of experience with, but I've mainly just sort of dipped my toe into Seaborn because it was more similar to what I knew.
Yeah.
Easier to get starting, but it sounds like HoloViews is a great place to play with as well.
Yeah, Seaborn looks nice also with all the prescriptions. Copy paste. Yeah, so it looks like not hearing lots of questions about Seaborn. Do you want to say a few words about what the Solar System Science Collaboration is focusing on in their sprint next week?
Yeah, we're focusing on grant proposals and people using DP0.3 because you can get some rough numbers. So an example, I'm part of the SSSC UK sort of in-kind contribution to build a component into the UK alert broker. That'll also be a package that can run on the Rubin Science platform to help you identify cometary activity in your sources. And so somebody said, so how many detections you're going to get a day? From like how many asteroid detections you're going to get in the first week per field for, you know, all these different numbers, right? And we don't actually have those numbers until DP0.3 because everything we've done has sort of been scaled from Rubin Sim, which is useful, but it doesn't necessarily give you, it gives you sort of the bulk statistics, but it doesn't give you necessarily that same granularness that you get. And so that's one of the things we're really focused on is that you can say, okay, great, how many with, you know, again, maybe there's a factor of 2 here, but like how many, the question we had was, are there more transient detections than solar system detections in the first week of the survey? Stephen Smart, who does supernova, thinks it's the reverse. And I was like, no, I think there's more transients. And he's like, I'm not sure. I think there might be more solar system detections unlinked until solar system processing picks it up. But we can look at that because we can actually go look at that in DP0.3. And so those are the things that people might want to write in their proposals of like actually rough numbers of detections of a certain population, right? And that you can actually go check, right? And so that's kind of exciting that you can sort of look at that. And so we want to help people get started and think about it and think about how it might be if they're proposals, because of most people I know are in the US. So thinking about NSF proposals, how DP0.3 can help you. So we want to have some dedicated time to think about that, to play around, and then have some project time where people can either work more using DP0.3 or other things they want to think about or talk about. But that's something like I wouldn't have been able to get a real answer. I would have been like, well, we can sort of scale it and do this. It's like, I'm going to load DP0.3 and you can actually calculate that and run the survey forward, right? Granted, there's some assumptions in Circa, which is the simulator that built this, is, you know, was still heavily in development. So there's some things that, you know, probably are maybe a factor 2, but still, it still gives you a much better answer to write in your NSF proposal. How many detections do you have in year 1? How much photometry do you have in year 1, year 2, year 3, to really argue the point, right? About what you're going to expect to see in the data release 1, right? The data previews, et cetera. So that's, I think, the really powerful thing of DP0.3. And so that's why I'm very excited to see it on the Rubin Science platform, because of that capability of actually understanding and making some plots you can throw in your proposal, right? And be like, here's what you get, right? Which is really nice. So that's the hope, is that we're helping people, encouraging people to use DP0.3 and think about it in terms of their proposals. And then also other people that are just getting started on projects, thinking about observing proposals in the spring, can do the same thing, right? Be like, here's everything we're going to find in year 1, year 2, and year 3, because we have plots.
Yes.
And you can, so that's kind of the thinking, is helping people dive in a little bit more concentrated, and then think about what are the use cases for DP0.3 that you might not have thought of, which until it was actually around, I was like, oh, it has all these really cool purposes that it's like, I thought I knew would be useful, but now actually being able to go, yeah, we have an answer. It's not me running some calculations, it's me running queries. So
yes. Good. That's the whole point of DP0.3.
Yeah.
I'm glad it's being used. And the question of, are there more moving objects or transients like in a single visit, like the alerts distribution? That's something that Yeah, I had estimated in a data management tech note on alerts key numbers. So I was just double checking, and sort of early estimates were like of the 10,000 alerts per visit, like 3,000 of them are moving objects. So
Right.
more than transients. But you also have the variable stars and the AGN in there. But yeah.
And so again, we're like, great. And then it's like, well, how many of them, when is it not associated? And so we can play forward and go, great. So, right, the asteroids will get picked up really quickly, but it'll take time for solar system processing to identify them. And so you can make plots of like how it will run, right? Of like, okay, when they move to a new patch of sky, there'll be a whole flood of things that are not known yet. And so we can look at that of how, for example, it would impact the broker of that things would be found, it would quiet down, and then there'd be a whole burst again of like things that would be solar system objects, for example. And so that's the nice thing that we can do. We can look at that in detail, or like how many on average, we know a rough idea of how many visits objects get. But now we can actually look at it and plot distributions, right? Okay, great. Well, we know on average, but now we can actually look at the distribution.
Yeah, that is cool. Well, I want to have you one more question, something that community science team hasn't much explored yet, the 1-year catalog. So we haven't done comparisons. We haven't really looked at how useful it is or done anything. And I was wondering if anyone in SSSC are they using the 1 year? Is it useful?
Yeah, the 1 year I think is useful. I think everyone's been playing around with the 10-year because the 10 year is bigger and fun. But yeah, the 1 year is actually the thing that I want to look at in and thinking about like telescope proposals and alert stream, right? And incremental templates. Like, okay, what's in play? Where it's a lot easier when you have 10 years to, right? And so looking at 1 year and particularly those populations where it matters, right? So I have a sense of that. I know what I get a sense of 10 years, but actually being able to compare the two is kind of useful. So that's my plan for the sprint of my project is I want to compare the two, like thinking about number of visits and like what is the difference between the observations. So yeah, so I think year one will have more value as people think about their proposals and things overall for the next couple of years, right? Or thinking about observing proposals where you're like, well, how would I argue for extra time if I think I need it? Because year 2 and year 3 or year 4, your objects will have whatever, right? More observations or baselines, etc. So comparing those two is something I think we're going to start doing, or people will start doing very quickly once they're familiar with everything.
Yeah, cool. Good. Great. Other questions for Meg? You've just got some compliments in the chat. Yeah, it's open. It's open to questions with compliments. Yeah.
So yeah, I'm in Slack. And again, if you're interested in solar system science and you're not part of the science collaboration, please join. We're very friendly. If you like anyone who likes solar system. But yeah, I just wanted to give you a sense of someone who's like sat down in the morning, was like, here's what I'm doing at like 6 a.m. before having to go teach, and be like, what can I do? And being like, this is what I would want to do on day, like, when there's a few years into the survey, like that's what I want to plot in the morning, right? And be like, cool, now what am I doing? My telescope proposal.
Yeah,
So it's really nice that we can test this now, which is fantastic. So again, big thank you to the Solar System Processing Group, everybody who was involved in making DP0.3, plus all the community science team for their great notebooks, and the database team and the RSP team for actually getting this put together. Right, I know it's a lot of effort, so we're really appreciative that it's happened and that it's really useful on top of it.
Yeah, useful all around. DP0.3 has sort of already been a pretty good success, I think. And like you're just getting started with it. So yeah, that's great. All right, I'm gonna pop up the breakouts. I think we don't have a ton of delegates left. Looks like we have lots of staff. That's okay, that happens. But would anyone like to hack on something in a breakout room today or continue discussions? this is the time where anyone who's here gets to suggest something, and we make or don't make breakout rooms depending on what people want to do today.
I could stay in the main room, but I want to create a catalog of regressors from scikit-learn and just run through all the regressors using DP0.2. And I'm looking for some suggestions for galaxies or stars or some data set that I can just start working through and just progress through all of the different regression techniques. And I just think that might be helpful in the long run.
Okay, so some DP0.2 stellar work, the stars, right? I'm not quite sure what you.
Or galaxies. I just need a data set to to test all the different regression methods. I've done it with Sloan data, but I just like to do it with some DP0. So to be like a demonstration catalog of all the different regression techniques in sklearn using some type of galaxy or stellar data from DP0.2.
So you need a data set from DP0.2 that you would be fitting with some function so that you can test different regression techniques.
Exactly. And if the data set I pick helps somebody, that would be even better.
Okay, interesting. So maybe like main sequence fitting?
Sure.
Yeah, okay place to start. Yeah, that's not quite my area, but maybe someone else here will have some ideas.
I think I'd just stay in the main room if somebody has some ideas.
Yeah, that sounds good. We can always make a breakout later if you want to keep chatting. And Douglas.
Oh yeah, I'm not sure if I'm. I may need a little help resolving the issue I'm having with logons onto the notebooks. I now can't. That I was mentioning in the chat window. Yeah.
Okay, so maybe one breakout room, and I'll try to help you with that.
Oh, that'd be great. Thanks.
Does anyone want to request any breakout rooms related to solar system science or seaborn? Because if there isn't, I think we can release Meg. You were saying you have like a list of other stuff that you wanted to do today.
Sure, I'm also happy just to hang out and listen, always learn. So I'm happy to just hang around in case people do have questions or again learn from what else is being discussed. So I'm happy to hang around until 6 or a little bit after my time, which is like 10, 15 minutes.
Okay, another 10 minutes. Yeah, sure. That gives people time to sort of just unmute and ask if they did have a question in the next 10 minutes. Oh, I see Greg's hand has gone up.
Sure. Meg, maybe you can tell us a little bit about what your science is. What kind of things do you anticipate to be revealed with the LSST, if you don't mind?
Sure, I'm not applying for NSF funding, so it's all good. You could apply to NSF anyway, it's fine. I'm interested in figuring out, I joke that I'm an outer solar systems astronomer, so I don't really care about the asteroids and anything else, but I pretend to for the Solar System Science Collaboration co-chair position. I'm like, I care about your things, but I really don't. So I'm interested in understanding Neptune's migration. I want to know if there's Planet 9. So my group is partially developing a slow-moving object pipeline to go beyond what Mario's solar system processing pipeline will find. And then debiasing the populations, or rather comparing to models, right? And so it's very hard to debias your orbital distribution and go the other way. It's a lot easier to take a model and orbital distribution, all physical characteristics distribution and bias that to what LSST should have found and compare. So my group got a link incubator to build Circa, which has helped create DP0.3, it sped up the code. And so now we can create DP0.3 in a day, in an hour, where it took a month, which is great. That it's now much faster. So the idea is to do that kind of comparison. So I'm really interested in population statistics, and then, finding weird stuff, because LSST is going to find lots of interesting weird stuff. So that's what I'm interested in, mainly for the outer solar system, but I'm slowly moving inward. So care about these centaurs now, the objects escaping from the Kuiper Belt, and you know, maybe I'll care about asteroids one day, but I still kind of pretend to care about them. But there are lots of asteroid science and lots of other science that'll go on. So that's been my main interest, still lie in the outer solar system.
Sounds great. Thank you.
I'm going to stop recording.